My guest and I recently co-authored a paper on portfolio optimization. Find out how we were able to outperform classical financial index tracking using D-Wave's hybrid solver and a little ingenuity. You may even hear Schrodinger's cat make a few background noises in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is Head of Financial Engineering and Quantum Developer at Multiverse Computing, Sam Palmer. Welcome to the show.
Hi, Konstantinos. Thanks for having me.
So full disclosure, Sam and I have known each other for quite a while now, and we've been working on a project together. And we have a paper out on archive that I'll link to in the show, but in the show notes. But before we get to all that, you have a really cool background. So I'd love to just give you a moment to tell us about how you ended up in your current position.
Yeah, so I studied my PhD in computer science, where I specialized in neural networks and customized hardware for derivatives pricing problems. Then after finishing my PhD, I was kind of looking for the next big thing. And quantum is already, becoming the next big thing. So this is where I thought this would be a really cool area to get into. So I started teaching myself more about quantum computing, quantum physics, and then combined that with my knowledge of financial engineering. And so this was when Multiverse was just starting hiring. So I saw them coming out of their incubator in Toronto, and I was like, okay, let's take a chance and apply to these guys to get into this really cool industry. And here we are today.
Yeah, it's a lot of fun hearing how people got into it. And we just did an episode about just becoming like a quantum coder because, there were no quantum coder tracks, you know, so you kind of have to assemble your own pathway. So I always love to hear. So thanks for sharing that. And of course, what you majored in is going to come in very handy with the types of things we're talking about today and the things you're working on. So let's talk a little bit about some basics here for listeners who don't know this, but just let's talk a little bit about portfolio optimization, just like a quick explanation for people to understand and like level set before we dig in a little deeper.
Yeah, so the basic formulation of portfolio optimization is we start off with a set of assets. So these are your stocks, and you have your returns on your stocks. So how much money they're going to make in the future. You can get this by any sort of forecasting, any sort of estimations. And then obviously there's some risk involved with these assets. So this is your covariance. So how much they are correlated with each other and how much, uncertainty there is in these price movements. So the idea of your traditional portfolio optimization problem is we want to maximize the returns, but then also minimize the amount of uncertainty in our portfolio, and then minimize also the amount of correlation between our assets in that portfolio. So that's the plain and simple objective here. And then obviously you start then being able to add more fancier constraints around these portfolios about how you would like these assets to be constructed and any other rules.
Yeah, so some of those rules could include things like how long you'd hold them, right? Or what you expect to get back.
Yeah, so we have some previous work where we've looked into these problems where we'll say you have to hold on to these assets for 30 days before you can rebalance your portfolio. But where this is more of a dynamic problem as well, where you have forecasts going long into time. Mm-hmm. So these are really complicated problems. And then you also have, other constraints where we might say we want to target the volatility of our portfolio. So maybe we say we don't want to maximize our returns as such, but we want to have like 10% risk and then maximize returns with respect to that. So this is some other work we've done with portfolio optimization as well. Okay. And then I think the other interesting set of constraints, which is very useful, is if you have different classes of assets. So you may want to invest in X amount in commodities, Y amount in bonds. So these are other constraints you can combine.
Okay. And when people hear about this, they have a hard time wrapping their head around what it means, because this has been done with classical computers for a while, obviously, and it has its challenges and limitations. So one of the limitations has been speed, if you're talking about a really big data set, right? So it could take, I don't know, dozens of hours, right, to run one of these if the data set is large enough. So some of the first successes you had in the past were with speeding it up, correct? Getting it done quicker with an annealer?
Yeah, so when we come to these large dynamic problems, there's a lot of combinations, and this is where it becomes very hard for the classical solvers to be able to do these problems. And the really cool thing about quantum annealing is that obviously when you find the ground state of these problems, so when we turn these problems into a quantum optimization problem, the runtime is static. It's not static, but it doesn't really change on the size of your problem. So that's the whole philosophy behind these quantum annealing optimization processes. So we don't encounter these scaling issues.
Yeah, yeah, that's important because obviously some data sets get so large that classical just can't do it ever. Basically, it would take till
Yeah,
the end of the universe to run it.
and I think a really other important point is that when you start adding some of these constraints, so when the problem becomes discrete, so we have very good classical solvers, but then when you start adding in these discrete constraints, this is when even the classical solvers become quite slow for what would be maybe a reasonable sized problem, and it's in these problems where the power of quantum really comes in because they're designed to handle these discrete style problems.
Yeah. So we brought all this basic knowledge to a recent project. I guess it's a long running project, so it took us about half a year to do. But so it's with a company that's named in the paper. So if you read the paper, you'll see the company name. The paper is called Financial Index Tracking via Quantum Computing with Cardinality Constraints. It rolls off the tongue like all paper titles. You know, it's like smooth like butter. Uh, and so there's a lot to talk about here. But when we started this project, the client wanted something a little different. They weren't concerned with speed, right? Because if they were doing things pretty quick already. So how did that hit you when we first began this? Because right away, almost on day one, they're like, "Yeah, we do this in 2 minutes." so so immediately we had to start thinking outside the box. So what's it like, hearing that and adapting and experiment over time?
Yeah, so I think this whole project we did was a great story of how we started off with something simple and then progressed to this paper. So where we started off simple was we had this. They obviously had this problem they could do very fast, but they wanted to test, how good was quantum. So even if we could have results which were, similar speed or, the speed ups weren't significant to how fast they're already doing things, um, is quantum actually a viable solution? And we were actually able to show them that we were able to match their state of the art convex solvers for solving these simple portfolio optimization problems. And I think what was the really cool result in that for us as well was that without any tuning of our optimizers, we were actually able to find better quality results than they were able to with the convex solver, due to the way we were able to create the problem in a discrete setting. And we can attribute this to the convex solvers. They'll be continuously, minimizing the gradient, and they'll be continually minimizing very, very small amounts. Whereas when we have the problem set in a discrete manner, you're kind of jumping out, so you're not getting caught up into like changing very small values all the time. You're almost changing the things that have the most impact. So this is where we actually saw a lot of value in demonstrating this discrete problem for the simple case. And then after that, the story was that how can we push it further? And I think this is where the really interesting work began.
Yeah, exactly. And as the title hints, we're going to get into cardinality constraints. So listeners should understand too that the applications here are for financial index tracking. So did you want to talk just about that for a moment before we get to cardinality constraints?
Yeah. So the index tracking is very similar to the portfolio optimization, except here the objective is we want to match the performance of an index. So typically indexes, they're not directly traded. You have to trade them through like an ETF, where the idea is these ETFs or these funds, what they're doing is they're buying all of these assets in the index and then compiling them to you and then selling you a small fraction of this product. So you're getting the same exposure. So the idea here is then we want to create a portfolio where we're using these assets to track the same exposure to this index. So this may be, the popular Nasdaq 100, or we've got the S&P 500, and then you've got the Russells, which go into the thousands of assets. And this is also where, as the title suggests, we go into the idea of these cardinality constraints, because if you're wanting to replicate these indexes, you might not want to buy all 500 assets of this index.
Yeah, and like historically, that's been really difficult to do. Classical, trying to match one of these, it's been a nightmare if you do a small subset. So we talked about in the past, you had to speed up. In this case, speed wasn't the issue. We wanted like better performance. So this approach, in a nutshell, we're able to use a tiny little percentage of the amount of assets and get very, very similar performance. So that's obviously very appealing. So did you want to talk a little bit about the numbers and the performance we achieved that way?
Yeah, so I think first of all, it's really important to highlight that when we introduce this problem of we only want to use this small subset of assets,
Mm-hmm.
this is what takes the problem from what we would call to be convex.
Mm-hmm.
So you can solve this using some very nice and efficient classical solvers, which we've just previously mentioned. The problem then becomes non-convex because we have to make these decisions. Do I want to buy an asset or not buy an asset? So you can't decide this using it as a continuous variable. It either has to be 1 or 0. So then this is where you then have to start relying on heuristic optimization methods, which can be non-exact, or they also become slow because you're having to evaluate your metric, your cost function every time. So the really cool result in this paper is that we were able to use the power of quantum to formulate the problem in such a way that the quantum processor can solve this optimization problem directly.
Okay, so and because we're doing this as an experiment that iterates over weeks and we refine it, that's a lot of hand holding, right? We're there, we're guiding the customer through. So what happens in the end? We end up building a tracking portfolio, and then we have to at some point enable the customer to do something with this, right? So do you want to talk a little bit about what happens at the end of such an experiment? Like what kind of uses they could apply directly on their own without us?
Yeah, so the results we saw were we were able to, as you said, like replicate these portfolios nearly exactly with just using a small amount of assets. So we were able to replicate the S&P 500 very, very closely with only 50 assets, and the Nasdaq 100 with only 25 assets. So this obviously has a great impact for when teams who are going to be building these ETFs, they're able to now create these products with less management overhead, only having to buy and manage 50 stocks, manage 50 exposures.
Mm-hmm.
So this actually makes the life of the fund a lot easier. And then on top of this, we also looked at enhancing the portfolios. So this means that we provide them the same exposure or very, very similar exposure to their underlying index, but we're improving on the risk profile of it. So in this way, we're saying you have the same exposure as the S&P 500, but you've actually got less risk in this portfolio of 50 assets than you would if you were to buy all 500. So this has really big implications for the customer. Now they can offer this product, but with less risk to themselves, but with still a similar exposure for the client.
Yeah, and a similar potential return. And we actually outperformed the risk profile of the target index, right?
Yeah, so this is where we saw like significant adaptations. We could customize a parameter which allowed us to change how much did you want to track the index. So if you wanted to get it very close, we were still outperforming the risk profile by 2 times with nearly exact tracking. And then, if you want to enhance on the returns of the index as well, so you're saying, I want to maybe get a better risk return profile in total, but still mimic some sort of behavior of the index. We were able to get like 4 times the risk return profile of the index.
Yeah. And I mean, that's obviously not insignificant. So we went from a world where portfolio optimization was considered faster, but not as accurate, right? Sharpie ratio accuracy was down by like 20% or something just a year ago. And now we're at a point where who cares about speed? We're outperforming it. So it's quite a different world. So where do you see this logically going as these machines get better? Because I mean, I know D-Wave's hybrid solver is going to get better soon. They're going to be upping its qubit count as always and improving its performance a bit. So what do you hope to see from the next iteration of the hybrid solver?
Yeah, so I think just sticking to relation to portfolio optimization problems and financial problems here is what I really hope to see now is that with more resources and better quality annealing solutions is that we can start to integrate more complicated constraints, because this is what makes the problems interesting. Mm-hmm. So at the moment, what we see is that with D-Wave, if we have too many constraints or we have to formulate the constraints in a way where we're using things called slack variables. So we have to apply additional variables which may not relate to the problem, but they relate to the constraints. These eat up resources, and also it makes finding the solution of the problem harder. So what we hope to see is that if we can find ground states more reliably, we're going to be able to satisfy the constraints more reliably, and also with more resources be able to embed larger constraints in our optimization problems.
Okay, and a few times over the course of the project, I know the customer would mention what's the actual cost, right, of running something like this. So how would that compare in terms of everything, time, effort, like typically, what other benefits can someone expect by going this approach instead of classical?
Yeah, so I think the first thing I'm going to say is a bit of a shameless plug here, but when we use the Multiverse Singularity optimization packages, where we provide access to a very simplified Python interface for creating these optimization problems, the time of development is minimal. Like if you have experience building an optimization problem using any other kind of coding package, you can use this, and then it compiles it and sends it to a quantum machine for optimization. So I would say with the tools we're developing now in-house and providing to customers, the cost of development is minimal. And then we're also seeing that as you said, as the quality of the annealing solutions increase, you have to do less and less calls or samples to the annealer. And so I think we costed it out to the client that I think the total solution may have cost them like 20 cents per time they wanted to run this. Mm-hmm. But obviously, this is only going to improve if they can just get the result perfectly with one sample. Then it may only cost them 1 cent.
Yeah,
So
that
this is our
insane.
advantage.
Yeah, that really is great. And for the record, I was going to ask you about that software platform, and we'll talk about it a little more. Yeah, we'll talk about it a little more too. So when someone engages with us to do something like this, they're getting a few things, right? So they're getting this experimental approach where we work with them, we listen to their constraints, we build this, we show them numbers week by week, and then eventually we get to the point where um, we're delivering things, right? So I know, like my team delivered a Power BI dashboard so they can observe all their results and analyze them and slice and dice them as they want. And part of the deliverable is also like a plugin for interacting with this data. So I don't know if you want to talk a little bit about what that all looks like, what you get in the end to play with after we leave the shop.
Yeah, so we provide multiple ways to use the tools. So we can offer we have an interface where we offer it through an Excel plugin.
Mm-hmm.
So you can access the quantum optimization just by opening up your spreadsheet, selecting your data with the plugin, and then you can send it off without a care in the world. And then you get back your results from this quantum optimization. Or if you're more inclined in the programmatic side, we offer these programmatic access packages. So through our library Singularity optimization, where you can code up these problems in your own way if you want, and then run these problems on the quantum. So we'll provide the code, the base code for the solution we provided. Then you also then have the power to modify these solutions, play around with these solutions, and even play around with your own problems with the Singularity access that you get at the end of the project as well.
Okay, and if you had to rate the abstracting away that your tool does, how would you rate that? Like, would you say that it abstracts away like a high, medium, or low amount of of like the complexity? Because a lot of these tools and interfaces for coding and quantum, they either get really down like analogous to old school machine language, or all the way up to something like more human readable. So how would you describe that for those who haven't seen the tool?
So I would definitely say the tool with the Excel plugin is obviously at the high level.
Mm-hmm. Yeah.
You have that. You don't even have to have programming experience to use this. You can just drag and drop, select your data, and then choose the product which you wanted to run it through, and then it's sent off, and then you get your results back. With the programming side, I would say it's still between the medium to high. So even with minimal experience in programming, it's still very accessible. We obviously provide basic examples to get you up and running. But the idea is that if you understand the basic concepts of programming and maybe a little bit about your problem, you should be able to get up and going within a day or two. And you can definitely get playing around with the problem straight away out of the box.
And what are your future plans for the software tool? Do you envision having access to it without like what we did with our whole project and the experimental approach? Or do you think it's going to stay for the foreseeable future as kind of like part of the deliverable?
Yeah, so this is definitely something we can deliver, and I think we have one customer who's already accessing Singularity just as a pure tool. So this can be just offered as a licensed tool for you to use in your company. For however you please, and you get access to the quantum machines through this, and you have the programmatic interface. If you were to develop more specialized applications for like plugins through the Excel, then that would be part of the experimental or a development cost. But you can just go straight for the license to use the product. So another really unique thing we offer, which you don't get with the access to the quantum machines, is with the access with the quantum providers, is we also offer tensor network optimization tools. So these are quantum inspired tools where they're running on classical machines. And we have some of the world experts actually developing these algorithms, which then you have access to through Singularity as well. So you can try out quantum versus quantum inspired. And then we'll also have plans to release quantum machine learning libraries as well. So you'll be able to access all of these state-of-the-art quantum machine learning models you see, but you don't have to necessarily be an expert in quantum or even an expert in quantum machine learning. So this is really our value proposition here, is that you don't have to be an expert to use any of these tools.
Oh, that's great. And are they going to be available like through cloud access, or would they have to be installed locally?
So we can provide the solutions either way. So the easiest package would be the cloud access, where all your data would be sent, all the data of your problem, but there's no worries there. We use really high standards of encryption and abstraction, so we never really know anything about the problems which are being sent.
It's tokenized, kind of, right? In a way.
Yeah.
Yeah.
Yeah, exactly. And then any data is, we shuffle it, we can encrypt it however the client needs, so we can customize some of the security needs if they were your worries. And then we can also do on-premises as well. So we could build your version of the Singularity servers on your servers, where we would provide our code, provide the code in Docker containers, or however you would like to run it. But obviously the code would be compiled, so abstracted in a way.
So yeah, and it's funny. So obviously we work together, and we're going to work together on other projects too. But I want to make sure people had a good glimpse into some of these great things that your team's working on there. So what are your feelings on quantum inspired in general? This is something that not too many people talk about, but if you had a gut feeling, how's that going to go over the next few years? Do you think quantum inspired is going to take off and become this viable thing, or will it be eventually so overshadowed by exponential growth of quantum power?
I definitely think over the next few years, quantum inspired is going to continue to be part of the trend. So we're obviously seeing, even with like big players like Microsoft, Microsoft is offering their quantum inspired solvers, where they're using customized FPGA hardware to simulate quantum annealing. And that's similar with, I think, is Toshiba as well.
Toshiba, the digital annealer, yeah.
Exactly. Yep. So we have these big players already offering some of these classical solutions. And I think with the quantum inspired algorithms, what they're doing is they're providing the gateway to quantum. So because I think you'll agree with me right now that gate model quantum computers aren't quite there yet to actually start getting real world, valuable, reliable results. And they're also very expensive to run if you were going to run it continuously on a problem, daily or minutely updates. So the idea is quantum inspired solutions, you can kind of get the data processing that you might get from the quantum, and maybe at the cost of that you're not getting that nanosecond speed, but you're getting a similar level of this, the complexity of how the data may be processed by a quantum machine. But then on top of that, I think what you're going to see, the trend is a lot of these hybrid methodologies. So where we'll use quantum inspired to simulate part of what we want to do on the quantum processor, but we might not be able to quite do it now. Or we might want to reduce our errors by doing some of it with the quantum inspired classically, and then put it on the quantum machine to finish off the runs. So I think this is going to be the trend where we're going to see this shift between quantum inspired and running these hybrid methodologies.
Yeah, that's great. Yeah, thanks. I appreciate that input. It's a funny chicken and egg problem, right? Like, so you got quantum inspired trying to outperform quantum, and then it just becomes this like who gave birth to whom. It's like, so I find that fascinating. And of course, hybrid is a big part of what we use, right? So the hybrid solver is key to the work here. Part of it's still done classically, part of it's done quantum, and I anticipate that's going to be forever. These machines are always going to be paired up. So if you had one hope for a dream future project, what would you say it is?
Ooh, that's a really tough one.
Like a dream, like a customer asked a question in a meeting and we were like, whoa, that's the one. That's the thing that we want to work on. If you just had anything off the top of your head.
So I'm trying to think about this. I think we're getting quite close to these with some current projects we've had from clients, which are looking more into around the derivatives pricing. So obviously that's a passion of mine from my my background before I joined Multiverse. So I really like seeing these projects where we're trying to solve these really hard partial differential equations using these quantum algorithms and trying to kind of innovate new ways to solve it. So if a client came to us and said, we want to solve this partial differential equation, we don't care how you do it, just do something really crazy. I think that would be my dream project where we can try some of these tensor network methods which may have not been tried before, or even trying very experimental quantum Monte Carlo methods using all different types of platforms. This would be really exciting.
Nice. Okay, cool. I was hoping for a good nerdy answer. Thank you. So thanks so much for coming on. And I encourage everyone to read our paper. It'll be linked in the show notes. And it's been a lot of fun working with you, sir, and having you on here. And I hope we get to do another project like this really soon.
Likewise. Thank you so much for having me. And yeah, I'm sure we'll see each other in the future. And I would love to come actually meet you in person. To see the grand 6 foot something of
6'6". That's right. Yeah, I think your boss was like surprised. Yeah, so Sam Mugel, he was like, "Whoa, yeah, yes." I expect we're going to be hanging before you know it.
Thank you so much.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. After completing a 6-month project together, Sam and I co-authored a paper called Financial Index Tracking via Quantum Computing with Cardinality Constraints. In the paper, we describe a hybrid quantum classical approach to financial index tracking portfolios that maximizes returns and minimizes risk. Running on D-Wave's hybrid solver, this approach builds investment portfolios that can generate the same financial returns as traditional portfolios, with significantly smaller groups of stocks. Replicating financial indexes using a limited subset of assets, known as cardinality constraints, has historically been an extremely difficult challenge for classical computers. How much smaller were the groups of stocks we used? The number of stocks in the NASDAQ 100 fund was 4 times smaller than in traditional portfolios, and 10 times smaller in the S&P 500 fund. The quantum built portfolios significantly outperformed the risk profile of the target index by up to 2x. This algorithm can be used for managing ETF funds, reducing overhead costs for financial managers while helping keep fees low for customers. Multiverse has developed an Excel plugin that makes it easy for users to run this algorithm without a programming interface. Multiverse also makes a version of its Singularity tool, allowing for more coding flexibility. That does it for this episode. Thanks to Sam Palmer for joining to discuss this method of portfolio optimization and multiverse computing. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at ConstantHacker. That's constant with a K, hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.